All right, how's it going? Good. All right. So about 2/3 of the class has done ODP 201 already. Well, we couldn't go through it yesterday because of connectivity, so let me run through the ODP today, start to finish, just to make sure everybody's seen it. So the assignment is write a function named sum that takes two integers and returns an int. Your responsibility in this is to create a function, okay, not a main program, a function in a file called sum.c, for example, just containing this one function, and I'll show you how to do this if you haven't already figured it out. The main program is being supplied by me. It's called a test bed. Okay, it's something that you take your function, you put it into this test apparatus, and it tests your program, your function, to see if it's correct or not. So the test bed is usually something like /temp/main.o. It's already compiled for you. To test your sum function, you should write your own main program. Okay, to test it for yourself, to convince yourself that it works, to see if there's any issues with it. And then once you're ready to submit it for grading, you link it with this test bed, and you do that linking by using a command like this. Okay, so you've done GCC before, but just a reminder, the -o says call the output file this. You can call it anything you want, okay, within reason. Don't call it test, because test is a keyword in Bash, but you can call it anything you want. That's going to be the executable program you're going to submit for assessment. This has got to be /temp/main.o, because that's the test bed. This can be anything that you want. You can call it, you know, haha.c, it doesn't matter. But whatever you called your file containing your sum function, that's what you put here. And this becomes your executable program. So then you assess it by just saying assess, and you have to put two arguments on assess. The first argument is the executable program, okay, the thing that will actually run if you just type the name. And the second argument is the source file, the thing containing your source code. So let's take a look at this. So I've written a version of sum.c, which is not perfect, because instead of just adding a and b, I'm adding a plus b times 0. But just to give you an idea. Okay, so I can compile this up, and it gives me an executable program, main. Now I can try to run main from here, but I shouldn't do that. If I try to run main, it gives me a seg fault. Main is not your program. Main is the test bed. Okay, and I'm not telling you how to use main. I'm not telling you what's in that test bed. Okay, sometimes I'll deliberately hide what's in that test bed, but you're not required to run main from the command line, right? You need to use the assess program. So assess main, and it'll say, oh, you got to specify a second argument. That's the source code. So assess main sum.c, and that takes me into the assessment system. So there's a short summary of commands. There's only 3 commands. There's G for grading, there's X to get out of there, and there's H, which shows you the 3 commands, including H. So there's not a whole lot of stuff you can do in here. You always get a little one-liner up here saying what it is you're about to assess. Okay? If you think you're assessing ODP 201 and this says ODP 202, write a function that simulates the universe, right? Don't go ahead and assess ODP 201. It's not going to work. Right? So exit out and go back and look at the assignment, look at the due dates, and so on and so forth. Okay? But we do want to assess ODB 201 because it's not due until tomorrow morning at 8, so we're still good. So I'm just going to go say grade. So I'm going to use the G command, and I get mostly 0 out of 10. Okay? One of them I happen to get 10 out of 10 despite the fact that my code was totally random. But my result is I've got 10 out of 50 now on this assignment. You should get 100% on every single ODP, okay? They're set up so that by the time you're ready to go on to the next class, right, tomorrow morning, for example, you should be able to do exactly what the ODP is asking you to do and get 100%. If you get 80%, there's something fundamental that you're not quite doing exactly right. And you shouldn't think, well, 80%, that's good enough. ODPs are only worth this much, and this, is a small piece of it, and so on. There's something fundamental in your understanding that you want to get corrected. Okay, so that's the time to go to your code and look through it again, compare it to the assignment, and then maybe start a discussion. Okay, or shoot an email. All right, so let's fix this up. So we'll go into sum.c. Hey, why did I type this? My cat walked across the keyboard while I was coding, so I'll fix that. And I'll redo my compilation. And I'll redo my assess. And now if I say grade, hey, I get 10 out of 10 on every single one. Did someone just come in and leave? Because I have more chairs. Okay. So if I do something like this, assess sum.c, and I try to grade, I'm going to get all kinds of weird stuff, right? But it doesn't have to be called main, right? Here I'm making an executable program called sum. That's fine. I can assess sum with sum.c, and I should still get my 10 out of 10. I have extra chairs if next time. Okay. Right. So things that I've seen happening is assessing the wrong program, right? Compiling and getting compile errors, like maybe you put in the wrong test bed. Right, and it gives me a compile error because it doesn't know about this, but then you go ahead and you try to assess main anyway, and main might have been like from the previous ODP, and you think your code is correct and you're not getting 10 out of 10, and the problem's not with the code itself, the problem's with the way that you're assessing, right? And probably about half the cases where people aren't getting 10 out of 10, it's not a problem with the code itself, it's a problem with the way that you're trying to get it assessed. You're not compiling it with the correct test bed, or you're getting a compile error, or you're using the wrong file name in the assess command, or things like that. So before you throw your hands in the air and say, I don't understand how to program, right, go back and look at the instructions, right, and see how you're using the assess command. So I'm going to say this for the first time in this course. If you're totally confounded on why you're not getting 10 out of 10, and you want me to try to help you, and it's after hours and I'm not here anymore, but you want to try to do this through email, here's what you need to do, okay? Show me your source code, sum.c, okay? Show me how you're compiling, right? Show me that line and any output that's produced by it. Show me the date just for the heck of it. Show me your assess command. Show me your G command with the, less than 10 out of 10s on those. Exit out of that. And now go back here, and depending on how you're doing this, right, grab all of this, copy it, go into Word or whatever your favorite word processor is, paste it, right? No, don't go into Word. Paste it as a plain text into an email. Right? Just go into email, send me a message, and just paste all of that. Okay? If you do that, I can look at what you've done and probably tell you what's going on. Okay? If you start doing screenshots, if you start turning this into a Word document and saving that as an attachment and things like that, it gets harder and harder for me to tell you what's going on. And if you don't have these pieces of information, if you just say, here's my code, what's wrong, I can't help you. Okay? So if you give me all this information, right, show me your code, make sure you show me how you compile, make sure you show me how you're running the assess command, and then the full shot of everything that happened in the assess session, right, there's a good chance I can look at it and say, oh, you forgot to do this, or you did that. Does that make sense? Okay. So any questions on the ODP, on assess, on any of that stuff? All good? All right. Any questions on anything else up to here? So let's start talking about data structures. I want to spend some time later this week talking about the structure statement and the type def statement in C and how to use those. And I want to talk about probably make files, because I've had a few requests already for a quick refresh on make files. But I'm going to do those later this week. And we're going to talk about PA1 later this week, which is already posted. And there's a quiz on Canvas that you have to do by the 11th, I think. And it's a one-question quiz just to make sure everybody knows how to get in there and do the quiz. And you shouldn't need to study to do it. I think it asks what course you're taking. And it's multiple choice. So I'll get to those later, but I want to jump into some data structure stuff right now, just to get us going in that direction. So let's start with arrays. So here's an array of 10 integers. And let me just draw a picture of what this might look like. So let's say we've got these aren't magic numbers, but let's just say there's 5 numbers in here that we've stored, 5, 4, 7, 2, 6, and then the last 5 entries we haven't put anything in particular in. Now, of course, there's numbers in here because there's no such thing as an empty memory location. Right? Every memory location on a computer has some value in it, and if we say what's the integer stored here, it will give us an integer value, but it will probably be something totally gibberish, right? But in some way we understand that we've stored 5 things in this array, and they're the numbers 5, 4, 7, 2, and 6. Okay. Suppose we want to search for a number in this array. We want to know, is the number 2 in this array? How would we go about doing that? What would our basic algorithm look like?
Start from the top, see if it's 2, go to the middle and see if that's 2.
Yeah.
Keep going till you find 2.
That's pretty much it, right? Start with the first element, see if that's the number we're looking for. If it's not, check the next element, check the next, check the next. If we eventually find our number, our search is true. Hey, it's in our array. If we don't find the number and we get to the end of our array, the number's not in our array. That's really our only choice. Now we could start at the end and we could move up, or we could start in the middle and go back, or we could be kind of weird and just search random numbers forever until we find it or we give up, right? But pretty much we've got to check every single number in there. And if we find, if we're looking for a 5 and we start in the beginning, hey, it only took us 1 operation to find it. If we're looking for a 15, we got to check every number in the array before we can say, no, it's not in there. Okay. That's fairly inefficient, but there's not a whole lot we can do about that. Okay, if this is just an array of numbers in no particular order, search is going to be expensive. So we'll formalize what this means, but let me sort of informally say this is order n. What do we mean by order n? It means that if there are n things in our array, it's going to take us roughly n operations to do our search. Right? Worst case being our number's not in the array anywhere, we've got to check all n elements. So if n is 5, it takes us roughly 5 operations to do our search. If n is 5 million, if there's 5 million numbers in there, it might take us 5 million operations to do our search. And yeah, sometimes we'll get lucky, it only takes one operation. Sometimes we're in the average, it only takes us half as many operations. But nominally speaking, it's on par with n. Okay, so we have this notion called big O notation, order of n. Big O of n is how complex a search is. And what it's really showing us is not how many milliseconds it's going to take to do a search, because that depends on your architecture, it depends what language you programmed in, what your clock speed is, and so on. What it's telling us is how many operations it's going to take. And more importantly, it's telling us if we double the size of our list, we're probably going to double the search time. We don't know if that search time is a microsecond or an hour. But we know that however long it takes to search this much data, if we double the amount of data, it's going to take us about twice as long. Okay, that's what we're really trying to capture with these orders of complexity. And we'll formalize this later on, but I just want to use this as kind of a motivation for where we're going from arrays to a better data structure. So search we can say is order n, right? It takes roughly as long as the amount of data. Okay, what about insert? What if we have our array here and we want to add a new number to our array? Suppose I want to add the number 8. Well, I would put it right here in this first unused location, right? I'd store an 8 here. But how do I know which locations are used and which locations are unused? Typically, remember, C arrays don't have an inherent length, right? We declared this array to have 10 integers associated with it, but there's nothing in the memory that says that there's only 10 things in here. And if we only fill in 5 numbers, there's nothing in the memory that says we've only got 5 numbers in our array. So we need some kind of variable like x length, which we could initialize to 5. And now if we want to add an 8, right, we just come down to element 0, 1, 2, 3, 4, 5. We store our number there, and we increment our length. And if we want to insert another number like 17, we come down to element 0, 1, 2, 3, 4, 5, 6. We put a 17 there, and we increment our length. So to do an insert is taking us a fixed number of operations, right? Look at this, go to that element in the array, copy our number into that element, increment the length. Okay, that's 4 operations. If we looked at it in assembly language, it might be 40 operations. If we wrote it in a very slick way, we might make it a single statement in C, which would be 1 operation, right? So, but it's order some constant number, right? And in particular, if x has 5 million numbers in it, and our length is 5 million, it still only takes me 4 operations to insert a new number. So we call this order 1. Order 1 is about the best you can hope for. It means it doesn't matter how much stuff is in your data set, doing this operation always takes a fixed amount of time. And even if it took 1 billion operations to do an insert, as long as it's always 1 billion, no matter how big the data is, it's still order 1. And the idea is if you get a fast enough computer, you can make this problem tractable no matter how much your data grows. So search is fairly expensive. Insert is very, very efficient. What about deletion? So suppose I want to delete the number 17 from this array. What do I have to do?
Find 17 first.
Okay, I find 17 first, and it's down there in that 6th location. How do I remove it from this array?
Replace it with the last element and then delete the last element too.
Oh, you're ahead of me. But that's good. But this is the last element in this case. Right, I'm deleting the number 17.
Since you don't care about anything after 8, couldn't you just decrement the length?
Yeah, in this case, since we're deleting the last thing, all we got to do is decrement the length. Changes to a 6. The 17 is still there, but we're acting like it's not part of the array anymore, because this says there's only 6 things in the array, which goes down through that H. Okay, but what if we want to delete something like the number 4? And now we can do what you suggested, right? So one possibility is to delete the 4 and shift everything up, but that's expensive, right? If there's a million things after that, we'd have to do a million copies. But we could, so let me just scratch this out. If we want to delete the 4, we could replace it with the last thing in our list, and then decrement the length again.
What if the array's sorted?
It's not sorted. It's ordered. We'll get to that next, though. Okay, so delete theoretically is order 1 after you search. So if someone says delete the 3rd element, it's very fast. If someone says delete the number 7, you've got to go through and search first and figure out where 7 is, and then delete it. So the big problem with arrays really has to do with searching. You throw a bunch of data in an array and then you want to look for something, it's expensive. You got to look at every single number in the array. Okay, so the way we deal with that is to have a sorted array. So suppose we just keep our data sorted. So we've got our array X, we know the length is 5, so there's 5 actual pieces of data in our array. How does this help us with searching?
Now you can do a binary search.
Yeah. Is that what you're going to say? Yeah. So if you did 224, you did a version of high-low. High-low is just a binary search. Right? You're basically searching for the number in the person's brain, and you're doing it by continually dividing the range of numbers in half. And so if you're searching for a number between 1 and a million, it only takes you 20 tries to figure out what the number is, or to decide that the number is not actually in the person's brain. So so we start with the first number and the last number, and we check the number in the middle, and we say, is this the number we're looking for? And if it is, we're done. But if it's not, if it's too big, right, if the number we're looking for is smaller than this, we can ignore half of the array. And we can say, okay, let's just search this half. And so each operation cuts your array size effectively in half. And so how many times can you cut an array of n elements in half before you get down to an array with a single element? And it's a log base 2. So search is on the order of log of n. It's log base 2, but usually we mean log base 2 in courses like this. And that's a whole lot better than order n. Right, so 1 billion numbers in your array, to do a search if it's unordered would take you up to 1 billion operations. To do a search if it's ordered will take you no more than 30 operations. Right, so that's a huge time saving. So we really like having our data sorted. But this raises a problem, because now if we want to insert something into our array, we can't just pop it onto the end. Suppose we want to insert the number 3. It's really got to go right here in between the 2 and the 5. Right? Otherwise our array is not sorted anymore. And there's no space for a 3 in between the 2 and the 5. So the only way we can insert that 3 is to make some space. And how do we make space? Well, first you have to move the 10 down, move the 7, move the 6, move the 5. And now this spot is available, and you can put your 3 there. But you've got to do this, shift everything down to open up a spot in the array wherever you want your new number to go. And that's good old order n. Now if I'm inserting the number 50, that's going to go at the end. I don't have to move anything. If I'm inserting a 1, I got to move everything. Right? So on average, it's n over 2, which is the same as order n. Double the amount of data, double the amount of time it takes to insert. And delete is going to be the same thing, because we can't take the last thing and pop it up into the middle of the array. Basically, if we want to delete the 6, we do that by shuffling everything up. We could get funny and we could put a flag here that says, okay, 6 isn't part of the array anymore, but now we're going to run out of memory. Right? To really be able to reclaim that space when we delete something, basically have to move everything back up. And so that's an order n. So we have a bit of a quandary here. If we have a plain old-fashioned array of unsorted data, it's expensive to search, but it's easy to insert and delete. It's fast to insert and delete. If we want to make it efficient to search, we have to sort the data, and now it's expensive to insert and delete. So you pay a penalty when you're searching, or you pay a penalty when you're modifying the data. So we'd like to get the best of both of those. And this is our first full-on data structure, and it's something called a linked list. And a linked list lets us basically do inserts and deletes in an efficient way. But it's not really going to help us with searches. And it'll be a few weeks before we actually address the search question. But we'd like to address this question of how could we put something in between two things that are already in our array without having to shuffle everything down in memory. So let's look at a faster insert. So how do arrays work? Go back to 270, if you've been there, and think about how you implement an array down at the assembly language, machine language, hardware level. So X is an array of 10 integers, and we want to access something like element 5. Let me ask you a question. If I say integer X bracket 10, and then I use the name of that array X, do you remember what that array's value is? If I were to print this, for example, if I were to pass it to a function, what does X actually refer to? The location of the first element, right? And that's all we ever get. X is a synonym for the address in memory where that first element is stored. Well, if that's all we know about X, how in the world do we locate element 1, the next element in the array? Yeah, we take this address and we add something to it. What do we add? We add however many bytes it takes to store an integer. So 32-bit machine, an integer is 4 bytes. So this is at basically X plus 4. Now C compiler does something funny. If you do X plus 1, it'll actually do X plus 4 because it knows X is integers. But in terms of just memory location, suppose that this is location 100. X element 1 will be stored at location 104. X2 will be stored at location 108. X5 will be stored at location 100 plus 5 times 4. Right, 2 times 4, 1 times 4, 0 times 4. So arrays work because each element has a predefined location in memory based on where the array starts. That's why arrays work. Right, that's why you can pass the address of the first element to a function, and the function can access all the other elements in the array. But this is also what makes it impossible to insert a number in between here and here. Because X bracket 1 is at location 104, X bracket 2 is at location 108, there's no space left in between these, right? Because this takes 4 bytes, and this takes 4 bytes. There's no memory in between them. And if I really want to insert something in between here, I've got no choice but to move everything down. So let's get rid of that tight connection between elements of our array and locations in memory. Let's break that. And let's say x0 is at location 100, x1 doesn't have to be at location 104. Could be somewhere else. x2 could be at location 108, or it could be somewhere else. So bear with me while we do this. All right, so suppose this is the current contents of our array X. And I want to insert a 6. Well, what I'd like to do, so let's say this is location 100, 104, 108. I'll be nice to you today and work in decimal, but normally we'll work in hex. So there's the addresses in memory of these 5 elements of our array. I'm going to take my 6 and I'm going to store it at location 120. But I'm going to say this is located in between this number and this number. In my array, this is the first number, the second number, but the third number is down here. And the fourth number is up here at 108, and the fifth and the sixth. So I'm no longer going to store my data necessarily sequentially in memory. Now how can I do that? Because unless I draw a bunch of arrows to say here's the first one and here's the second one, but now we come down here for the third one and then we come up here for the fourth. And if I could draw these arrows somehow inside the computer, I could put my numbers anywhere I want. Right? That's exactly what we're going to do. Okay? And that's going to give us what we call a linked list. The list, and these are the links. Alright, so you got the basic setup. So let me show you some pictures. Here's what our linked list is going to look like. So instead of just having a number, four, 5, 7, 11, 13, I'm also going to have another thing associated with each number, which is basically something that tells me where the next number in our list is. So I'm going to think of it as an arrow right now. I'm just going to have this thing point to the next piece of our list. And the 13 is the last thing in our list, so where should that arrow point? Well, we need something special. We need a flag of some sort, which says there's nothing after this. This is the end of the list. So I'm just going to write null to say there's no arrow at all coming from the 13. It's the end of the list. And I somehow need to know where this begins, so I don't know. I'll have something called header that tells me where this begins. It's like the 100 where the X array began in memory. We've got to have some way to get to the beginning of this list. So we have something that tells us this is the first thing in the list. If we want to know what the next number in the list is, we look at this arrow and say, oh, next thing is a 5. And once we're at that 5, there's something associated with that tells us where the next thing in the list is. Oh, it's a 7. And the next thing is an 11. And the next thing is a 13. And the next thing, oh, there is no next thing. That's the end of the list. And this completely captures this original array containing 4, 5, 7, 11, and 13. Okay, so now we want to insert a 6. If you're going to create a new piece of data, I'm going to call this a node that contains a 6. what do I have to do to put this 6 into that list and keep everything sorted?
Drop from 5 to 6 and then 6 to 7.
Yeah. All I got to do is when I come out of 5, instead of going straight to 7, 5 should point to this, and 6 should point to 7. So I still need to find where I want to do this insert first, right? I'm going to have to search through here. But when I get to the 7, right, I know it's got to come right before the 7. So I do the following. 1, I take the previous node, and instead of pointing to 7, I point to our new node. And then our new node, I have that point where the previous node used to point. And it's basically 2 operations. And the list is still sorted. Now it's 4, 5, 6, 7, 11, 13. But I didn't have to move all these other things around in memory in order to insert the 6 between the 5 and the 7. Right? Why? Because these don't have to be, this doesn't have to come at a physical memory location in between this and this. This can be anywhere in the machine's memory because I have something pointing to it, and this is pointing to the thing that comes next. Okay, that's the essence of a linked list. That's the next 4 weeks of this course, basically. So we're obviously going to keep working on this and building on it. But that's the essential idea of a linked list. Instead of having fixed locations in memory, each piece of data also tells us where the next data is. And so now let's delete 11. So how do we remove an 11 from the list?
Make 7 point to 13.
Just make 7 point to 13. Get rid of this. Change that. 11 is gone. It's still sitting in memory somewhere. But if we move through our list from the header, we're going to see a 4, a 5, a 6, a 7, a 13. And the 11 is magically gone. And once we knew where we wanted to delete, it took 1 operation, basically. Change this to point wherever this was pointing. So insert and delete are very efficient now. Search is still terrible.
Do you include search in the requirements to insert?
Yeah, you do have to find where you want to do the insert. But once we fix the search problem, then that won't be an issue. But that's 4 weeks away. So what we've solved here is that if we know where we want to insert or delete, those have become order 1 operations. So our next question is, how do we implement this in a computer? How do we create these blocks with arrows pointing to other blocks?
Structure.
Sorry?
Structure.
Yeah, we can use structures. We don't have to. We can actually do it without. But for PA1, we are going to use structures. But in some way, each of these pieces of data needs to have multiple pieces to it. It needs to have the actual number that we're storing if we're making a list of numbers. It's got to have something that refers to the next entry in the list. And it's also going to need something to tell us whether or not it's actually in use. For example, when we deleted this 11, all we did was change this node's pointer to point to the 13. We didn't actually do anything else with this node. Right? It happens to still be pointing to 13 also, but it's not part of the list. But we'd like to know that this is not part of the list so that we could reuse this piece of memory sometime. So we probably need some kind of flag that says, you know, is this actually part of our list, or is this spare and available for use? So that the next time we want to insert something, we could reclaim this 11. Right? So let's just do one more insert. Let's insert, I didn't leave my, let's insert 4.5. So we could draw a new box and put a 4.5 in it, but we've already got a box here that's not in use, right? So here's what I can do. I can change this to 4.5, and I want to put it in between the 4 and the 5. So I'm going to change the 4 and have that point to 4.5. And then I'm going to change 4.5 to point to the thing that comes after it, which is 5. Okay, so this is horribly spaghetti-ish for us, but it's nothing for a computer. So what's in our list? We start with the header. There's a 4. That leads us to the next node, which is 4.5. That leads us to the next node, which is 5, which takes us to 6, which takes us to 7, which takes us to 13, which is the end of the list. So we're going to write code to do this. And we're going to write code twice to do this. PA1 and PA2 are both going to be basically the same behavior, but different implementations. PA2, we're going to use pointers and ampersands and stars and mallocs and all kinds of things that will potentially ruin your night, but in a good way. But PA1, we're not going to do that. Okay, PA1, we're not going to use anything other than arrays and structures. Because PA1, I want you to think about and get comfortable with this idea of manipulating these nodes, right? So this is what I'm calling a node. This thing that has a piece of data and a pointer to another node. I want you to work and think about and get comfortable with the idea of manipulating these nodes to build a list and to manipulate the list, to insert and delete and search. But we're going to do it in a way that doesn't deal with memory, addresses, and pointers, and ampersands, and so on. We're going to do it with good old arrays. So how do we do that? Well, here's a picture. We're going to make an array, and each entry in this array is going to have 3 pieces. So this is going to be an array of structures. And I don't know how big I say to make it. I do something on the assignment. But 3 pieces to each entry in the array. So this is entry 0, 1, 2, and so on. So the first piece we can call data. That's the actual number that we're storing in our list. The next piece of an array entry we're going to call next. And this basically tells us the index of the next entry in the list. And the last piece is just a flag called valid, which tells us whether or not an entry in this array is actually part of the list or not. So suppose we have the following. So 2 points to 5, points to 10, points to 15, and 15 doesn't point anywhere. So suppose we have a list of 4 numbers. All right, here's how we could implement this in this array. So our first, header is 0. That tells us our first node is going to be at location 0 in this array. The data there is going to be a 2. It's going to be valid. And it's going to point to the next node, which is a 5. So we can store our 5 at index 1. So the next field of this first node is a 1. That says go to index 1, that's the next node. and that's got a 5, it's valid, and let's say that points to 2, which has a 10, and that's valid, and it points to 3, which has a 15, and that's valid, and the next field after that is null. So this is a straightforward representation of this list as 4 elements in this array. Okay. So if we were reading this in code, we'd say header is 0, our first piece of data is a 2. The next piece of data is whatever's stored at index 1, that's a 5. The next piece of data is what's stored at index 2, that's a 10. The next piece is at index 3, that's a 15. The next piece is at index null, that doesn't exist, that's the end of our list. So now, if we want to do an insert, say we want to add a 7, right? So we create a new piece of data, 7. We mark it as valid. We take the previous node 5, and we say that should point to this new node. So here's where the node 5 is stored. Currently it points to 2. Instead, it should point to 4, because that's where our 7 is stored. So that sets up this. And then 7 should point where that previous node was pointing. That previous node was pointing to 2, so we'll have 7 point to 2. And we're done. So now if our code goes through and says, tell me what's in the list, well, we start with header 0, that's a 2, followed by a 5, followed by index 4 is a 7, followed by index 2 is a 10, followed by 15. That's the end of the list. Okay, if you can do these kinds of games, right, you're good for the next 4 weeks. Right, because seriously, that's what we're going to be concentrating on. Well, maybe 3 weeks. Writing the code to do this is, a programming exercise. But writing the code to implement this is not the same as learning what a linked list is, right? Learning what a linked list is understanding these pictures, or understanding the representation of an array with 3 pieces to each element, and how we can do inserts and deletes and searches using either these pictures or these structures. All right, so think about that. Tomorrow we will go through PA1 in detail, and it'll be basically talking about how we're going to implement a linked list using this kind of array of structures. So we'll start working with that, and I'll post a new ODP, which will get you started on doing some structure work, and we'll do some review of structures. Yeah?
So I'm just kind of interested in garbage collection and complex. So if you
Hold on, let me stop this.